I'm going to present our recent work on video QA. We call it the invariant grounding for video question answering. Video QA is to predict the answer of the given question regarding the content of the video. Above is the input video. We can see that there is a man doing the long jump in the field. And there is a question, what is the man doing? It's easy for us to tell the answer is jump. However, this can be a problem of the current video QA prediction, because even the state-of-art model deems this is a race. Why is that? We ascribe such false prediction to the impact of the background scene, which is the question invariant frame. In contrast to the causal scene that contains sufficient information to answer the question, its complement scene, aka the background, deviates answer prediction through the statistical shortcut. That is, there are too many training samples of someone race on the track, so that once model notices there is a track scene, it will directly put race as the answer, regardless of the content of the causal scene. We quantify such superior correlation between the complement scene and the answer by calculating their local mutual information, briefly LMI. Intuitively, LMI depicts how likely answer would be given the object in the scene. In this case, it shows the most likely answer given only track as the input scene. Since the shortcut sample are learned first and the model prefers sample of LMI, in our case, race, instead of the actual answer, which has a low LMI, jump, information on the trivial stream can prevail and mislead to the false answer. From the perspective of the causality, we formulate the causal graph to address this problem. Given the question, we can define a causal scene that distills the question relevant information from the video, and leaving the rest of the video as a complement scene. The answer A is determined by the question Q and the causal scene C, which reflects the visual linguistic alignment. Considering the example above, C is the last three frames that explain why jump is labeled as ground truth answer to answer the question. The dash row between the complement T and the causal scene C summarizes the possible probabilistic dependency between C and T. Such dependencies are usually caused by selection bias during the data collection or annotation. In this work, our goal is to keep the answering A away from the influence of complement scene. According to the causal graph, we notice that the ground truth answer A is independent of the visual complement T, only when conditioned on the question Q and the causal scene C. This probabilistic independency indicates the invariance, that is, the relation between CQ pair and A are invariant regarding of the change in complement scene T, which highlights that finding the causal scene and pair it with the question is the key to shield answering A from the influence of T. The traditional video query paradigm is the combination of the video question encoder and answer decoder. The encoder encapsulates the scene of the video and the linguistic semantics of the question as a representation, whereas the answer decoder exploits its representation to model the visual linguistic alignment and then yield an answer. In comparison to the conventional method, our method, we call it IGV, owns some very intriguing properties. The first is the visual explainability, that is to answer which visual scene are the right reason for the right answering. So when asking what is the man doing in this case, the model should attend the jump event present in the last three clips rather than the track complement scene in the first two clips. It should also have the ability of introspective learning, that is to double-check how would the predictive answer change if the causal scene were absent. In other words, it should fail to answer the question if the causal scene were removed. It should also have the generalized ability to answer how would the predictive answer respond to the change of the superior correlation, as the superior correlation are poorly generalized to the open world scenarios. The model should instead latch on the causal visual linguistic alignments that is more stable across different environments. Here we introduce the IGV more concretely. It integrates two additional modules in addition to the video QA backbone, a grounding indicator and a scene intervener. Specifically, the grounding indicator learns to identify the causal scene for the given question and leave the rest as a complement. Then, we collect the visual clip from the other training video to compose the memory bank of the complement stratification. For the causal part of interest, the scene interventor conducts the causal intervention on its complement, that is, replace it with the stratification sampled from the memory bank and compose the intervened videos. After pairing the causal complement and the intervening scene with the question, We feed them into the backbone model to obtain 3 corresponding predictions. First is the causal prediction, which approaches the auto answer so as to achieve the visual explainability. Second is the complement prediction, which contains no clue to the ground truth answer, thus enforces the backbone model to perform introspective reasoning. The third is the invariant prediction, which is constant with the causal prediction across different invariant complements. And we enforce this invariant prediction consistent across the different environments. Let's see some results. We can see that IGV become new SOTA in all 3 benchmark datasets. By nature, our IGV is orthogonal to the backbone design. Therefore, we test IGV on different backbone video QA model, and we notice a constant improvement for every situation. And here is the application study. Thanks, that's all.